Hi everyone, this is Matt Tuchel in Intro Stats, and today we're looking at a problem from my book, in Introduction to Statistics for Community College Students. And today we're going to be looking at section 3F, number 14. So again, this is a section where we're starting to put together a one population hypothesis test. We've been going over one population proportion and one population mean tests in this chapter. So this looks like a one population proportion test. Notice we're talking about one single percentage, it looks like. So let's read the question and see if we can go ahead and do this. So it says an online source suggests that 1 out of every 3 people in the U.S. have a high blood pressure, and the population proportion of U.S. adults is 33.3%. Another website disagrees with this and claims that the true percentage of U.S. adults with high blood pressures is actually dramatically lower than 1 in 3, lower than 33.3%. So a random sample was taken of 500 U.S. adults and found that 165 of them had high blood pressure. Use the StatCato printout below and a 10% significance level to test the claim that less than 33.3% of U.S. adults have high blood pressure. Okay. So the one thing to keep in mind here is, yes, we are doing a hypothesis test, but the computer part of the hypothesis test has already been done for us. If you notice, they already put this data into StatCato, and we got a StatCato printout right here. That means you don't have to do anything in terms of putting the data into StatCato, though we could do that, but the StatCato is just going to give us what's already printed here. So our job here is to try to figure out what all these numbers are telling us. Okay, so you don't have to do anything in terms of getting StatCato up and running or putting the data into StatCato. This has already been done for us. Okay. So we got to start with the claim. It says here, use a 10% significance level to test the claim that less than 33.3% of U.S. adults have high blood pressure. So it sounds like a less than claim, right? The population percentage is less than 33.3%, or the population proportion, if I convert this into a proportion, it'd be 0.333. So we're going to start there. So let's do that. So we're going to start with our claim. So pi is less than 0.333. Pi, or you could use p also. P is fine. Some books use p, some books use pi for a population proportion. And less than, notice again, points to the left. Always keep your letter, if you're doing a one population test, keep your letter on the left and your numbers on the right. And then again, less than points to the left. So it should say pi is less than 0.333. And that is our claim. That's what they want us to, that's what they're claiming is true. Now, we need to know the opposing view. So what's the opposing view? Well, they said that the other view is that it didn't say that it's greater than 33%. It said that it's exactly 33.3%. So the opposing view in this problem was not actually greater than or equal to. It was actually just equal to. And that's very common, especially in this kind of stuff. So now once we have the claim and the opposing view of the claim, now we have to decide which one's the null and which one's the alternative. Remember, claim has nothing to do with it. Okay, it has to do with the symbol. Equal to, or a symbol with equal to, is always the null. Anything that does not have an equal to, like not equal or less than or greater than, is always an alternative, HA. So what we see is this first one, the claim, has actually got to be HA because the symbol is less than. So HA is going to be pi is less than 0.333. And again, the other one is an equal to 0.333. That's got to be a null hypothesis because of the equal to. Again, it has nothing to do with what's the claim. The claim could be the null or the alternative. So we write down the claim, we write down the opposite of the claim, then we decide what's the null and alternative. All right, so it looks pretty good. This would be a left-tailed test, a one population proportion left-tailed test. We have one proportion that we're dealing with. And again, the alternative hypothesis is a less than sign pointing to the left. This would be a left-tailed test. So all the calculations were done in the left tail. Okay, let's take a look. So let's take a look at our assumptions here. Did we pass all the assumptions? Let's take a look and see. So the assumptions for a one population proportion test, a traditional one, this is not randomized simulation. They're using a test statistic and critical value. So was it random? Was it a random sample? Yes, they said it was a random sample. Did we have at least 10 successes and at least 10 failures? So did we have at least 10 people with high blood pressure? Yes, we had 165 people with high blood pressure. Did we have at least 10 people in the sample data that did not have high blood pressure? Yes, 500 minus 165 is definitely a lot bigger than 10. So we passed that assumption. Now, are these people independent of each other? We can't have people that were like in the same family or related or things like that. So that's a very big and important assumption to think about, is independence. I think we're good because we have a random sample of only 500 people out of every adult in the US. So we're talking about a huge population. A small random sample out of a very, very large population, millions and millions of people. The chances of us getting family members in these 500 is very, very slim. So we're probably okay with independence. Usually a small random sample out of a very big population, usually it passes the independent assumption. Okay, so it looks like we're good with assumptions. Now we just got to make sense of this. Okay, we got our null and alternative hypothesis. So first thing we want to know now is, does the sample data significantly disagree with the null hypothesis? Well, our sample proportion, 1 to 65 divided by 500, is actually 0.33. That, on the face looks very close to 0.333 or 33.3%. These look actually very close. They don't look very different. But again, don't make a snap decision. That's what your p-value and test statistics are for. That's what's going to tell you if these are significantly different or not. They are a little bit different, but not very. They don't look like very much. Let's take a look at the test statistic and the p-value. So the critical value is 0.1282. So think of it like a curve, right? We have a curve. And we're trying to get, we know that the left tail starts at negative 2.82. Now, again, for our test statistic to be significant, it has to fall in the left tail. In other words, it would have to be to the left of negative 1.282 on the number line. So like negative 1.5, negative 2, negative 2.5, negative 3, negative 3.5, those would all be considered significant. What was our z-test statistic? Our z-test statistic was negative 0.142. That's very close to 0. So we are not in the left tail, right? We are not in the left tail. We are basically at 0.142, which is actually to the right of negative 2.82 on the number line. So we're not in the left tail. So this is telling us that this sample data does not significantly disagree with the null hypothesis. Right? Our test statistic did not fall in the left tail. Now, could this sample data just be a result of sampling variability? Definitely. Look at the p-value. We got a 44.34% p-value. That's very big. That's 44%. That's definitely a lot bigger than the 10% significance level. So we definitely have a very high p-value. And remember, if you have a low p-value, lower than the significance level, then it's unlikely to be sampling variability. High p-value means it could be sampling variability. Doesn't guarantee it is, but it could be. So this definitely is a could be situation. This little bit difference between 0.33 and 0.333 is probably the result of just sampling variability. Okay, so let's go back here and see if we can finish this problem up. So we got our samples that we tested these. We got the assumptions. Our test statistic sentence, the sample proportion 0.33 was only 0.142 standard errors below the population proportion 0.333. Notice it says below because in the test statistic it was negative 0.142. So that means remember, a z-test statistic is number of standard errors above or below. So in this case, it's below because it's a negative. In which case, All right, our sample data does not significantly disagree. We said it does not fall in the tail. We have very high p-values, so if the null is true, there's a 44% probability of getting the sample data or more extreme by sampling variability. That's your p-value sentence. This could be sampling variability because the p-value is very high. Reject or fail to reject. Again, we have a high p-value, so we're going to fail to reject the null hypothesis. So our conclusion. We have a high p-value and the claim was HA, right? Our claim was alternative less than. So that's going to mean that our claim was HA. So when we failed to reject the null, but our claim was the opposite of the null. All right, so this is a not support situation. So we do not have evidence to support the claim that the percentage of U.S. adults with high blood pressure has decreased. In other words, the high blood pressure rate may still be 33.3%, and there's no evidence that it has decreased. Okay, so even though our sample data was slightly lower than 0.333, it was not very much lower, and it probably is just the result of a little bit of sampling variability. Okay, so remember, in these problems where you have the StatCato printout, you don't need to do anything. You just need to interpret the numbers and write your sentences. All right, so I hope that helpful. This was section 3F, number 14.